Hi everyone, welcome back. In the first two episodes, we met the segment anything, or SAM, and we saw where it struggled. Today, we talk about its impact. What does SAM really give us in healthcare? The first question that we are going to answer is what are the practical applications? The authors mention some applications, but this model has a much broader potential, especially as a component in the larger system, similar to how CLEEP or DAL-E are used for vision language tasks.
Wait, clip? That's the one that matches images to text captions, right?
Exactly, and just like CLEEP can be plugged into other models for broader tasks, this model could serve as a flexible module. For example, for faster dataset annotation, as medical image annotation is time-consuming, and this model can help speed that up significantly. Or automated segmentation. It could power the segmentation part of an imaging workflow from diagnosis to surgical planning, or even for interfacing with LLMs. Think of it as giving a language model eyes to interpret image and generate reports. Generally speaking, we can integrate this model in different workflows. And the next question is, what questions remain unanswered in this paper? While promising, this paper raises several open questions. For example, can we make the encoder smaller without a big performance drop? We should think about knowledge distillation for this part or teach the student models. Or can we add prompt layering to guide the model more interactively? Sometimes we don't want to click on the image. Instead, we want to say, segment this part of the body. Or is it possible to use this model on new datasets without heavy fine-tuning? The short answer is yes, but not always. And lastly, how well does it work with low resolution or noisy images, which are common in real-world clinical settings? I tried this is not good. And the last question for this paper is, how practical is it for healthcare? Actually, it's already great for 2D image annotations like X-ray segmentation, but not for regions that are completely blurred or somehow blurred. If the boundaries are clear, then segmenting can segment that part very good. But if we want to extend this part to 3D images like MRIs or CTs, the task is a bit challenging. One practical route is to use the encoder to extract features and then train a lightweight decoder customized for medical tasks.
Wait, is the decoder like a translator that turns features into predictions?
Exactly, you can think of the encoder as extracting meaning from the image, and decoder decides what to do with the meaning, like segmenting a tumor or detecting anomalies. However, we should keep in mind that there are limitations. It might struggle with noisy or low-resolution scans, and fine-tuning could be needed. But that also risks losing the general knowledge of the model already has. Also, inference time, especially for 3D volumes, is a concern. It's not yet fast enough for real-time use in a busy clinical setting.
So, is it usable or not?
It's not plug and play yet, but it's definitely promising, especially for building general segmentation models across multiple imaging types, something that's often needed in research hospitals or multi-site studies with varied data qualities. All in all, we can say if you are an AI researcher, think about working on model compression, visual prompting, or zero-shot transfer for medical data. These are hot areas where you can contribute real value. If you are in clinical space, consider how this could reduce annotation time or support broader imaging workflows across departments.
Should we give it a recommendation score?
Sure, I would give it a recommendation score of 7 out of 10 for AI researchers. There is a strong foundation, but lots of room to innovate. For medical communities, I would go higher, like 9 out of 10, because of its potential to ease the challenges of working with diverse, often unlabeled image datasets. That was the last part of this paper, Zora. Ready to move on?
Always. Let's keep exploring.
See you next time!